Okay, welcome back. We are moving on to shoving 8.3, 8.4, and 8.5 together, so I'm going to rush through 8.3 and 4, mostly because I think you'll be able to handle rushing through those two, and then 8.5 is really like the applications of everything I introduced in 8.3. And it should feel very similar to what we did earlier over the last two lectures, and so that's why I think we can handle going through all three really quickly. The overall idea is that we're applying the same sort of criterion, same sort of methods we were using for analytic functions in the last couple sections to now Fourier series functions in these sections. And I want to talk about the name here. I'm giving it the Fourier series transform name. Some people would argue in favor of calling this a Fourier transform. Other people would argue against calling it a Fourier transform. I think in general, I feel like it is a Fourier transform, and I think most people would agree with me, but sometimes when you say Fourier transform, you truly mean the transform over the entire real line. And we'll get there eventually in this course, but what you're referring to here is a transform over a finite interval or a compact interval, and the transform you recover out of that, or rather the series you recover, is the Fourier series. And so that's what we're going to recover here is a Fourier series, the same way that you've already seen the Fourier series. But basically, we're just going to define the same sort of stuff we did with analytic series as now the Fourier series. So jumping down a little bit, I'm just going to define the Fourier series transform. And unfortunately, I use the same calligraphic F to define the transform as I do to define the space itself. Just note that every time there's a subscript by the F, that's referring to a Fourier space. It's a space of, square integrable functions over that interval. And then the calligraphic F without any subscript on it is going to be the transform itself. And so just like with the analytic functions, we can take the transform of a function by interpreting the series of that function, and then the transform is just extracting the coefficients and placing them into a vector. So the Fourier series transform is the interpretation of a function as an infinitely long vector of its Fourier series coefficients. And so it's just like we had with the power series transform, but now we're working with the Fourier series instead, and we're interpreting it as a vector. We can then interpret the reconstruction, or rather the inverse Fourier series transform on any given vector in this nice L2 space, little L2 space, just as computing the dot product with an infinitely long vector of exponentials, and that will exactly recover our Fourier series, and then we're back in the common space of functions that we would think about it. So just like before, we just want to send ourselves into this notion of this is now a space of infinitely long vectors. And because of that, I can do some very interesting things with differential equations. So let's look at the theorem. The first theorem is pretty important. It's the Fourier series transform of linear operators. So it's just the same way we were doing before. I can represent any linear operator acting on my function now as a matrix acting on the Fourier vector. However, I interpret the Fourier vector. So I have an infinitely large matrix on the Fourier vector, and I can compute these just by, I have an n on the left-hand side and an n on the right-hand side. So I compute the interaction of L on that specific basis element of the Fourier series, and then I re-represent that. I guess the lower subscript should be minus infinity here, right? I re-represent that as the Fourier series. I'm asking what are the Fourier series coefficients in the variable m. I'm summing over the variable m. What are the Fourier coefficients of whatever this image is? And that's actually how I gain a matrix. So my matrix m sub n, right? That matrix is exactly those Fourier coefficients. So it looks like this. It's kind of ugly, right? But once you compute, if you compute each one of these separately and represent the image as a Fourier series, that's where you recover the m and n entries. And this is what the matrix looks like if you put the 0, 0 right in the middle and 0, 1 to the right, and so on. So this is just a nice little maybe reference for you to refer to if you ever forget how to calculate these. You calculate them right there on the top, and then put those numbers into the matrix here. So in this setting, we get the derivative, which we've seen before, right? This was one of those exercises that we tackled already. The derivative in a Fourier space over x1 minus x0, right? If those are the bounds of my Fourier space, I can always factor kind of this term as just a constant that depends on the space I've chosen. But then the derivative itself is a diagonal matrix, and that's really why we decided the Fourier series was so powerful. Is that the derivative is now a diagonal matrix. What do we like about diagonal matrices? Well, if we take functions of diagonal matrices, then we just have to take functions of the diagonal entries. And so this actually starts to head into the territory of PDEs, where we might want to consider the exponential matrix, or the matrix exponential of the derivative for PDE settings since something like, partial t of an unknown y, if I say that that's equal to dy, where the d on the right hand side is my derivative matrix here, then our Cauchy problems still apply, and we can solve this particular Cauchy problem, which now is actually a PDE. We can solve it with the exponential matrix, or the matrix exponential. And so that's why, primarily why Fourier series, Fourier transform is relevant. It is for PDE's reasons, but we'll see that there are some good applications to ODEs as well. Just tell yourself that if you're headed in the direction of PDEs at some point in your future, all of this is incredibly relevant, and probably more relevant in that setting. But yeah, the matrix, so the derivative matrix in this Fourier series transform sense is diagonal, and we can see right in the middle, thanks to this 0, the derivative is not invertible, and we all know that because when we take a derivative, we lose constants. And of course, the 0 term of the Fourier series, e to the 0 times something, is exactly the constant function 1. And so this perfectly represents that we lose information about constants when we take derivatives, the 0 right in the middle there. But aside from that, it's invertible, right? Okay, so we can also represent multiplication by a function the same way we did for analytic functions. So in the Fourier space, it gets a little bit uglier, but not terrible. If we have a Fourier series representation of a function, so called g of x my function, and take its Fourier series representation, there's my a sub n's. Okay, what's actually happening here is think about the Fourier series transform of g now as this infinitely long vector, a0, a negative 1, a positive 1, dot, 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 dot. And what's going on, if we look at each row here, that is my vector. That is my Fourier series transform vector version of g, but it's been reversed. This is like g, but reversed. And we're getting really close to this notion of convolutions, right? Because I think any of you that have dealt with convolutions, this word reversed should start to trigger something in your mind saying, oh, this is just like convolutions. So actually, this definitely is hinting at convolutions for us. But we didn't necessarily calculate this matrix starting with convolutions, right? We're not going to say, oh, I'm going to produce some sort of convolution here. That's not what we're trying to do. What we actually did to calculate this matrix is precisely, what I have on the screen right now is we calculated the action of that vector, really multiplication by that vector on e to the in, and then calculated the new Fourier series for that and plugged everything into this matrix, which is a direct result of theorem 5.2.7, if you go back to that theorem. And kind of what we recovered out of that was this thing that's hinting at convolutions. And one of your exercises will be to kind of talk about this in the language of convolutions. So that's something to look forward to. And there's a proof, right? So you can see the proof. It has nothing to do with convolutions here. We're just straightforward figuring out what the entries should look like. Okay, so because of that, we have our matrix M, which corresponds to multiplication by a function. We have our matrix D, which corresponds to derivatives. And just as before, we can now convert any differential equation, linear differential equation, into a matrix, an infinitely large matrix, acting on an infinite vector for whatever y would map into, and then our infinite vector for what f would map into. And the solution maps are exactly the same. We're going to take the pseudo inverse of this matrix L. We're going to act it on some arbitrary v that's actually in our space. The particular solutions are going to be given by precisely acting L inverse on the right-hand side of our original ODE, which is f of f, capital F of lowercase f, and then the general solution is the two of them added together. So this should feel very similar to what we were doing before, and in particular, there's nothing special about this section compared to then when we get to applications of this, or actually approximating solutions with this method. Section 8.4 is just a remark, right? So I'm remarking on what it means to actually have solutions with this method. This remark exists because this method won't necessarily find solutions as k tends to infinity. If I head onwards, when I get to my next section where I'm trying to approximate these by truncating at k and heading to infinity, we don't actually receive solutions the same way we did before. And that's a bad thing, right? And the reason comes down to this remark right here. So we have actually an initial assumption before we're allowed to consider the Fourier series, right? Because the Fourier series necessarily is a restrictive space. Now, the space of analytic functions is also restrictive, but it's a very large space. It's an incredibly large space, at least when it corresponds to Fourier to differential equations. Space of Fourier series has very specific restrictions right here. It's periodic boundary conditions. Every time I reconstruct something with the Fourier series, and you saw this when you were working with your Fourier series, it reconstructs objects periodically. And that's not a good thing if the solution to our differential equation is not periodic. And so we can really only use these particular methods in the situations where we're actually given a boundary value problem, and the boundary values in the boundary value problem are periodic. And so that's something to keep in mind, and that's actually why the entire chapter 9 exists. That's why our Laplace transform and Fourier transform that we'll see in chapter 9 exist. It's to try to remedy this. So what I say is there are two sometimes possible workarounds. If we start with an IVP, then one of our boundary values can be at t0, because everything happens at t0 for an IVP. Then we can fix a maximum future time and like grab a value slightly higher than that, and just assume that the solution is periodic for times greater than that. And what that allows me to do is say, okay, I'm periodic on this like super interval, but I'm only going to look at my function on a restriction of that interval. That's not a very good approach, but it works a little bit. And then similarly, if I have like maybe non-periodic boundary conditions at x0, x1, then once again I make my interval just slightly larger in both directions, and I decide to say, okay, it's periodic on this like super interval, but it's non-periodic where I care about it, and I restrict it again. But once again, I think neither of these two cases are actually very good workarounds, and they're only sometimes possible to pull this off. So these methods aren't as powerful as the ones that we just encountered, but it's good to get used to maybe how these things work, because actually once we get to PDEs, they are incredibly powerful. And so it's a really funny thing. And then there's this last notion of letting epsilon go to infinity in both of those cases, in which case I'm really working with a Fourier series over the intervals t0 to infinity, or minus infinity to plus infinity. And in these settings, periodicity is no longer important, because what does it mean to be periodic at infinity? Well, it's not really periodic, right? Like being periodic over an infinite interval means that, like, sure, my function's allowed to repeat itself once I reach infinity, which is never going to happen. So that's really the true workaround to these, is by either working on this interval of t0 to infinity or minus infinity to infinity. And exactly this first case gives me the Laplace transform, and the second case gives me the Fourier transform, where I no longer worry about this word series. So like the true Fourier transform considers a domain of minus infinity to infinity, and the true Laplace transform considers t0 to infinity. That's chapter 9 though, and we'll just stick to this chapter for now, where this thing isn't perfect. So moving onwards, for when this isn't perfect, we have the Galerkin method. And Galerkin methods as a whole are much broader than what we're going to see here, but this is like one subset of what people often call the Galerkin method. And the Galerkin method is to basically take a space. You have a space where you have an orthonormal basis, and it's separable, so you have an infinite orthonormal basis. If you decide to project onto finitely many of those infinitely many orthonormal bases, then you convert your problem to a linear algebra problem, solve it, and then send yourself back, and you end up with an approximation, which is just what we did in the analytic functions setting. But our basis is not orthonormal in the analytic function setting. Our basis is orthonormal in the Fourier series setting. And Galerkin, technically by its name, only applies to orthonormal settings. Okay, so that's what we have here. Is we're basically going to do the same thing we did with the analytic functions, but now we're working in this orthonormal space of the Fourier space. And that's very useful. What we're going to do then is truncate the same way, right? We're truncating our Fourier series at k and minus k. And I'm going to call these functions t sub deg k, t because these are called trigonometric polynomials. Trigonometric because if I wanted to, I could rewrite these in terms of sines and cosines, right? And those are our trigonometric functions. So that's why we call these trigonometric polynomials of degree k. And in many ways, this is the natural k truncation of the Fourier space. So if we took k all the way out to infinity, we would recover the Fourier space. But we just want to be aware that this is actually a 2k plus 1 dimensional space, even though it looks like it's calling a k truncation, you might think it's just k dimensional, and that's not true. So this is always odd dimension, because we have an equal number of positive and negative n, and then we have 0 in the middle. So we always have an odd dimension of this space. And then we look at the definition of the k truncated Fourier series transforms, where I'm just like with the analytic cases, I'm truncating by a k. So I'm stopping at a k here, and all I'm going to do is get the 2k plus 1 length vector, which is exactly those entries of my Fourier series. Once again, we recover a pseudo-inverse, because if I decide to take f inverse of f sub k, then that's only going to give me a trigonometric polynomial. It won't give me the entire Fourier series, and so I have a pseudo-inverse, which is why I gain an approximation and not the function as a whole. And then our derivative is precisely the same diagonal derivative matrix we had before, but now I've truncated it at 2k plus 1 by 2k plus 1. It's a square matrix that's only that large. Same thing happens if I'm multiplying by g. I have to truncate at 2k plus 1 for my matrix. And because of all this, now I'm legitimately sitting inside of the linear algebra territory. And just like what we got used to with analytic functions, we do the same thing with the Fourier functions. And we start with a linear ODE and construct a single matrix which represents the entire left-hand side of that ODE. And then we convert ourselves to a matrix vector equation in 2k plus 1 dimensions. LK is a matrix. F sub ky is a vector. It's an unknown vector. F sub k of f is a known vector. Hence the solution should be y is f sub k inverse, but that's a pseudo-inverse of L sub k inverse f sub k of f. And in fact, that's a particular solution. That's only an approximate particular solution. But that's what we want to think about, is we're still going to do this idea of applying our linear algebra knowledge to these ODEs. And there you can see the same stuff I had before, where I have a homogeneous solution given by, well, we're going to act the identity minus the pseudo-inverse and see what that gives me on some arbitrary vector, because this automatically gives me the null space. And then this approximate particular solution is going to be given by what I've just drawn for you. And then the general solution you recover by adding them together. And by the approximate solutions, we mean the exact same thing we had before. So to use Galerkin's method, we need a boundary value problem with periodic boundary conditions. Remember, I said that as the entire point of section 8.4, and I want to be clear about that again. To use these methods, we must have a BVP with periodic boundary values. Okay? So to use it, you must have a BVP with periodic boundary values, which we thankfully do in this case. So there's my BVP with periodic boundary values. What does periodic boundary values look like? It just means that the value of the solution on one end of the boundary is equal to the value on the other end of the boundary, same for every derivative. Okay, so the boundary values are each derivative is equal to itself at the boundary, including the zeroth derivative. Okay, so if I'm going to apply these, then I should rewrite sine and cosine in terms of its Fourier series, which I do right here. So, and especially out to two Fourier modes. So k equals 2 here, which means that I actually have a vector of length 2 times k plus 1. So 2 times 2 plus 1, it's a vector of length 5. So f2 of sine is I over 2, 0, 1, 0, negative 1, 0. And I think my negative 1. Yeah, my negative 1 and 1 look like they're negative because I had a sign. I had a negative I over here because it's in the denominator, and I brought it up to the numerator. And then I have cosine, I have 0, 1, 0, 1, 0. So you could calculate each of these out for your Fourier series. And then that gives me the matrix which corresponds to multiplication by sine. Right? So it might not look like it, but here, what's going on here is that this, we're called the multiplication matrix by sine, is I'm taking this vector and I'm plugging it in horizontally into my matrix, and then it's getting shifted. As I move up, it shifts to the left. As I move down, it shifts to the right. So that's why we see this diagonal behavior of the 1 and the negative 1. And in particular, the entire vector you can see horizontally in the middle. So that's how you construct the multiplication vector, and then the derivative, or the multiplication matrix, and then the derivative matrix is thankfully very easy. It's just the truncated derivative matrix. And because I have 2 derivatives in my original ODE, 2 derivatives right there, I have to square it, right? It's the truncated derivative matrix squared. And if I compute those matrices out, I see the following, I recover the following matrix, which represents L. So this is a representation of my differential equation up to 2 Fourier modes, which is actually a 5-dimensional vector space. So that's the representation of the ODE that I was considering. And then I can go through the process of computing the homogeneous solution. And it turns out that L is fully invertible which means that the homogeneous solution will just be 0. We want to interpret this as saying there are no trigonometric polynomials of degree 2 which are solutions to the homogeneous equation, because I've restricted myself to degree 2. So no trigonometric polynomials of degree 2 are solutions to the homogeneous equation. An approximate particular solution can be calculated just using my formula, which you'll recall was, so the right-hand side is this. And so I'm taking L inverse of this. L is a 5 by 5 matrix. I'm computing L inverse of that, and that's giving me a vector, gives a vector of Fourier coefficients. So if I reinterpret the vector of Fourier coefficients that gives me, I end up with my particular solution right here. And you could leave it as exponentials if you want to. Cosine and sine both have representations as exponentials. And so if we add the 0 to my particular solution, I gain a general solution, which looks exactly like this. I mean, it's a boundary value problem, so like the homogeneous solution should be fixed for a boundary value problem in most cases. And then what we have here is a plot of our approximate solution in red to the true solution in black. And I do want to comment, because a lot of you might think that they look so similar that they are the same solution. They're not. The true solution in black is not the same solution as what we've just drawn in red. But they agree so well already up to just 2 Fourier modes that they're basically on top of each other. So this procedure is a really good approximation procedure when it works. But the only problem is, for it to work, you need to start with a periodic boundary value problem. But then you get just absolutely amazing approximations in like no time at all. And so that's one example for it. And then let's cover one other example. Here I have in this example I have something which I represent up to 2 Fourier modes as well. And so cosine of 2x we want to interpret as a Fourier series function. What is the if I write cosine of 2x on minus pi to pi, this is like e to the 2ix minus plus e to the negative 2ix all over 2. And so what does this look like as a Fourier series? It's still 1/2, but now I have 1, 0, 0, 0, 1. So this is my cosine vector in this setting, because why did my ones move up? It's because the frequency increased. And you can just go ahead and calculate the Fourier series for each of these functions when you want to. And thankfully my coefficients over here, I don't even multiply by anything. So all I have is 2 derivatives and the identity, because on y there I just have the identity. So I calculate my derivative matrix, I add y onto it, square it. I recover this as my L. So this is now a matrix which fully represents the left-hand side as an ODE. And we're going to notice that we do not have periodic boundary conditions. But that's why I said we're going to use the Galerkin's method on the interval minus pi to pi, because my boundary conditions are inside of minus pi to pi. So I can, if I have a non-trivial, maybe I'll mention that here, if I have a non-trivial, meaning non-zero, not equals 0, homogeneous solution, I can fit non-trivial boundary conditions. And so in this case, I will have a non-trivial homogeneous solution, and we're going to find that out in just a bit. Yeah, if I calculate the null space of this matrix, I think a lot of you can already start to see where is the null space on this matrix. Well, it's on that row and it's on that row. Well, I guess it's on columns. So it's on this column and it's on this column. Hence, the null space is precisely the vector 0, C1, 0, C2, 0. That's the null space, which corresponds to those functions, if I want to represent them as real functions, or these functions, right? So that's the null space of L. And because I have a free choice of C1 and C2, I can actually use that to fit the boundary conditions. I go through the same process on cosine to give me my particular solution, which my particular solution here is negative 1/3 cosine 2x. But now I have my 2 free parameters for my homogeneous, where I can fit the boundary conditions. The boundary conditions were 0 and 1, and if I fit those boundary conditions, I recover the following as my solution. So there's the actual solution, approximated up to 2 Fourier modes of this non-trivial boundary value problem. And I think that's really interesting that we can actually fit some non-trivial boundary value problems as long as we find the right elements in our homogeneous solution. So if I scroll down now, there you can see the approximation of the Galerkin representation with the true function. And once again, these are not the same function. The approximation is just so good that it looks like they're the same function. And so this is why Galerkin truncations are fantastic when they work, and it's really sad when they don't. But that's all I have. Thanks for sticking through 3 sections with me. I'll see you in class. Bye.